The structure of 2-hydroxybenzene carboxylic acid is shown. Give the equation for the reaction of 2-hydroxybenzene carboxylic acid with methanol. In your equation, include the skeletal formula of the organic product. So I'm just going to work through it without doing the skeletal formulas just yet, so that I can then turn them into skeletal formulas. So methanol is an alcohol. So the alcohol would react with the carboxylic acid part of 2-hydroxybenzoic acid. It's not going to react with another alcohol. And we're going to eliminate water. So we're going to join these two parts together. So if we think we've got C double bond O there, I'm going to join that to the O of methanol, and the hydroxy group's going to remain, and we're going to get water. But we need to turn that into skeletal formula. So 2-hydroxybenzoic acid and methanol. Although it doesn't ask us to do the skeletal formula of the reactants, but I am doing the skeletal formula for everything. And then we're going to go to, just watch out that you don't draw that C at the ester, and then the methyl group on the ester plus water. We've drawn our structures. Aspirin is produced from 2-hydroxybenzene carboxylic acid by reaction with ethanoic anhydride. So we've got our 2-hydroxybenzene carboxylic acid and then ethanoic anhydride. This time ethanoic anhydride is the acid part, so we're going to leave the Q group alone, the acid, and we're going to connect to the ethanoate, and that'll leave us with ethanoic acid as our other product. So method, add 2-hydroxybenzene carboxylic acid to a conical flask. Add excess ethanoic anhydride and a few drops of concentrated phosphoric acid. Heat the flask to 85 degrees C for 10 minutes. Cool the flask and pour it onto 150 centimetres cubed of cold water. Filter and wash the solid aspirin. Recrystallise the aspirin using a 50-50 mixture of water and ethanol and check the purity. Aspirin can also be produced by reacting 2-hydroxybenzene carboxylic acid with ethanoyl chloride. State why ethanoic anhydride is preferred. Well, there's lots of reasons here, but one of them would be that ethanoic anhydride is less corrosive than ethanoyl chloride. And it does not form HCl in the reaction, which is obviously not as, we don't want to form HCl. HCl is a strong acid. We wouldn't want to form that in our reaction. It's forming a weak acid instead. Give the name of the mechanism for 2-hydroxybenzene carboxylic acid. So what we've got here is we've got an alcohol with a lone pair attacking a delta plus carbon, nucleophilic attack, and we're going to add it on and then eliminate the acid. So it's nucleophilic addition, elimination. The role of the concentrated phosphoric acid, it's not in the equation, so it would be a catalyst. Why is reflux not essential when the flask is heated to 85 degrees C for 10 minutes? Well, we only need reflux if there's a chance that we might lose our reactants or products by evaporation, so we want to keep condensing them. And so we wouldn't need it if the boiling points of the things that we've got are higher than the temperature we're heating to. So the boiling points of reactants and products are above 85 degrees C. Complete and label the diagram to show how the impure solid is filtered. So we're going to be filtering under vacuum pressure, so a vacuum filtration under reduced pressure. So this would be off to our vacuum pump. We need to draw a Buchner funnel. So we've got a flat bottomed funnel. Don't close the bottom of the funnel off. Remember, you've got to allow the cross-sectional diagram's got to allow for things to go through, but we do want to sinter the bottom of that funnel, put holes in the bottom of that funnel, and then we want to put a piece of filter paper on top of the funnel. So that's our filter paper. And this is our Buchner funnel. Right now, that vacuum pump's not going to work because there's a big hole. So we need to put a bung in here. So not cutting through the funnel, but sealing the top of our flask. So we've got a filter paper, we've got our funnel, we've got a bung in our flask. And we should be able to filter. Suggest the identity of 2 impurities present in the filtered solid aspirin before it is washed. So want to go back and think about making our aspirin. Anything that we used, so there may be unreacted 2-hydroxybenzene carboxylic acid, there may be ethanoic anhydride, there may be phosphoric acid, and there may be this product ethanoic acid that we've made. All of these could be impurities in our sample. So any 2 impurities that we might have in there. So the other product, ethanoic acid, and then we used a phosphoric acid catalyst, but you could put in there ethanoic anhydride, 2-hydroxybenzene carboxylic acid, any of the things that were used. Describe the recrystallization process to purify the aspirin. So our solvent, if we scroll all the way back, was a 50-50 mixture of water and ethanol. So the first thing we want to do is dissolve our impure aspirin. In the minimum amount, so the minimum quantity required to get it to dissolve of hot solvent, and the solvent is water and ethanol in this case. It's really important that you say hot and you say the minimum amount. You then want to filter the solution whilst hot, and what you're doing there is removing any bits that didn't dissolve, so removing any insoluble, things that didn't dissolve, impurities. Now you've got this solution that's been filtered of any bits that hadn't dissolved. You need to allow it to crystallize, so you want to cool the solution to allow crystals to form. And these are our crystals of aspirin. And then we're going to filter it again, but this time under reduced pressure, the Buchner funnel. And while we're filtering it, we're going to wash our aspirin with cold solvent so it doesn't redissolve. And that's going to wash away any soluble impurities. And then dry the aspirin. State the physical property that is measured to check the purity of the aspirin and describe 2 ways the results would show it's impure. Well, it's a solid, so we would use its melting point to check its purity. And if it's impure, the melting point would be lower than the data book value. And the sample would melt over a range of temperatures rather than a very specific temperature. So over a range rather than sharply at the data book value.